All right, let's just dive right into this explainer. Today, we're tackling something absolutely fundamental, yet totally mind-bending about quantum computing: absolute reversibility. You know the hype. Quantum is going to revolutionize everything. But to really grasp how, we actually have to completely rewire our brains regarding how information is processed. We're looking at why quantum computers don't just do things a million times faster, but do them completely differently by literally never throwing information away. So let's get into it. Here's our roadmap for today's explainer. We'll start with the quantum leap, move into the reversibility reveal, crack open the quantum toolbox, look at building reversible circuits, and finally wrap up with the future of computing. Starting off with Section 1, the quantum leap, bits versus qubits. The difference here is just stark. Think about the laptop or phone you're using right now. It relies on classical bits that act like rigid light switches, right? They're locked firmly into a state of either 0 or 1. But quantum computers use qubits, and qubits are a whole different beast. They act way more like a spinning coin. While that coin is spinning, it isn't just heads or tails. It exists in this fluid state of probabilities, a superposition of both at once. And here is the kicker, the secret we're unpacking today. Classical gates are inherently irreversible because they constantly lose information, while quantum gates, they are always reversible. Always. Moving right along to Section 2, the reversibility reveal, preserving information. So this begs a huge question, right? Why are quantum gates always reversible? Why couldn't a super advanced quantum computer just delete or overwrite data the exact same way our phones do every single second of the day? I mean, when you clear your browser history, that data is physically discarded by classical logic gates. So why can't a quantum processor just do that? Well, it comes down to the fact that classical gates literally throw information away. Take a classical AND gate, for example. It takes two input bits, smashes them together, and spits out a single output bit. If that output is 0, you literally have no way of knowing what those original two inputs were. The past is completely erased. But quantum gates? They are bound by the strict laws of quantum mechanics to preserve every ounce of information. Instead of smashing data together, quantum gates just smoothly rotate a qubit's state within a geometric space. Because it's just a rotation, the information is just moved around. It's never destroyed. And that brings us to a massively important concept in quantum physics, the unitary operation. See, because quantum gates are essentially unitary matrices, they naturally preserve the total probability of all possible outcomes. Zero information is lost. What this means in practice is wild. You can take any quantum process, apply the exact inverse of that operation, and just run the whole thing completely backward. It's literally like being able to unbake a cake just by reversing your stirring motions perfectly. Every single step inside a quantum computer has to adhere to this rule. All right, let's crack open Section 3, the quantum toolbox, meet the gates. I absolutely love this quote. To compute in parallel, we must first learn to dance between parallel worlds. It just perfectly captures what we're actually doing when we manipulate these qubits. If we want to harness that insane parallel processing power of a quantum computer, we first have to coax our qubits out of our boring, definite, classical world and get them dancing in the strange, probabilistic realm of quantum mechanics. And our main tool for starting that dance? That would be the Hadamard gate. You can kind of think of the Hadamard as the ultimate coin flipper. So instead of just flipping a bit from a 0 to a 1 like a standard classical NOT gate would do, the Hadamard gate basically flicks the coin and sets it spinning. It takes a definite boring state and shoves it into a perfect 50-50 superposition. And to be clear, this isn't just a random guess. It is a highly precise mathematical state where that qubit exists as both 0 and 1 at the exact same time. It's honestly kind of funny how ridiculously simple this H symbol looks on a standard circuit diagram, considering it acts as the literal gateway to quantum superposition. It's usually the very first gate we apply in an algorithm to pull the computer out of the classical realm. And remember that rule about reversibility? Because the Hadamard is a unitary gate, if you apply it twice, it completely reverses itself. It catches that spinning coin, stops it, and perfectly returns it to its original definite state. But of course, we need more than just the Hadamard. We've got a whole toolbox of these reversible operations. You've got the poly-X gate, which flips the qubit state entirely, kind of like a classical NOT gate. The poly-Z gate changes the quantum phase of a qubit without actually flipping its probability, which is a concept that literally has no classical equivalent. Then you get into the multi-qubit stuff, like the C-NOT gate, which flips a target qubit but only if a control qubit is activated, or the swap gate, which exactly exchanges the states of two different qubits. All of these tools let us flip, rotate, and interact our qubits without ever erasing their history. Take that swap gate, for instance. It's just an intersecting cross that cleanly trades the information between two qubits, which is super useful for routing data through the processor. But again, because it's a unitary operation, it perfectly preserves those past states. If you run the swap gate a second time, boom, they unswap, putting your data precisely back where it started. Which brings us to Section 4, Building Reversible Circuits, Entanglement in Action. This specific three-step sequence is easily one of the most important building blocks in all of quantum computing. If you chain a Hadamard gate to put that first qubit into superposition, and then immediately follow it with a CNOT gate to link it to a second qubit, you create what's known as a Bell state. And this right here is pure magic. It creates entanglement. Those two qubits are now inextricably linked, behaving as a single connected system no matter how far apart they are physically. But even with all this spooky action going on, because every single gate we used is reversible, this entire incredible entanglement process can still be flawlessly undone at any moment. Now, you might be wondering, what if we just need to do some regular classical style math? We already established that classical AND gates are irreversible, right? Well, scientists are clever. They developed workarounds, like the Fredkin gate, also known as the controlled swap gate. It conditionally flips the second and third qubits based entirely on the state of the first one. By using complex multi-qubit gates exactly like this one, we can successfully simulate classical logic inside a quantum computer. We get our AND or OR gates, but we remain 100% reversible, preserving every single drop of information along the way. Let's wrap things up with Section 5, the future of computing, why this matters. Look, we are currently living in the era of noisy quantum hardware. Researchers are actively running these reversible gates on real cloud platforms from companies like IBM and SpinQ as we speak. But this timeline is moving incredibly fast. Between 2029 and 2032, we are expecting the arrival of fault-tolerant processors that can actually handle robust quantum error correction. And looking past 2033, we are staring down the barrel of a literal quantum internet and massive AI integration. The completely reversible nature of quantum gates is the exact underlying mechanics that will make all of these exponential leaps possible. So, I want to leave you with this final, somewhat mind-blowing thought. Since the very architecture of these gates directly reflects the unbroken, perfectly reversible laws of quantum physics itself, you really have to wonder what previously impossible problems they might help us solve. I mean, if our machines can finally process reality the exact same way the universe actually operates, without ever losing a single trace of history, what incredible secrets are we about to unlock? Thank you so much for joining us on this explainer, and keep your curiosity spinning.